Good evening, ladies and gentlemen. My name is Agarwal, and I'm going to talk about the future of AI. I want you to imagine that you've just applied for a job. You've taken the time to fill out your application, tailor your CV, only to receive an automated rejection email a few days later, simply stating, "We will not be taking your application further." You try again at a different place, only to get the same result. Each time, there's no reason given, no explanation, no context why. You try again and again, and eventually, you start to wonder, is it my qualifications, my skills, or something else entirely? But this scenario isn't just a hypothetical. Approximately 88% of recruiters currently use AI at some level, and AI has a fundamental flaw. It simply cannot tell us why it makes the decisions that it makes. In fact, in the United States, a class action lawsuit is currently working its way through the courts, in which a man alleges that an AI hiring system discriminated against him and countless others on the basis of race, age, and disability. And this isn't the only context where AI is being used to make life-changing decisions without any explanation being given. From insurance and loan assessments, medical diagnosis, even AI warfare systems used for target acquisition in Iran. Needless to say, without fully understanding the reasoning behind these decisions, it just doesn't make sense to blindly trust them. Now, while this does raise lots of interesting moral and legal questions about liability, this isn't an ethics or governance talk. Today, I want to talk to you about AI interpretability, a field that I believe is going to define the future of AI and is a solution to how we can better understand AI and its decision making. But first, we need to take a brief look at the mathematical functioning behind AI that explains why even its creators struggle to understand it. Most of the AI that we use today is built on deep neural networks. The name gives us a clue. These systems are loosely inspired by the human brain. They consist of artificial neurons, up to millions or billions of them, arranged in layers, where each layer is connected to the next. The basic process is surprisingly straightforward. Data, such as an image, prompt, or file, enters the first layer of neurons. Each connection between neurons has a weight, signifying relative importance. So at each neuron, a little calculation takes place. The inputs are multiplied by the weights, and we add a bias, a little offset term. The output passes through a function, and that goes to the next layer, where the process repeats, and again to the next layer, and the next, until eventually we get our final answer at the output layer. Beneath all that complexity, it's really just layers of essentially simple calculations, shaped purely by billions of parameters, the weights and biases. Input times weight plus bias, wrapped in a function. A formula, if you will. However, right now, this just sounds like any other algorithm that can be audited and understood, step by step and line by line, which it would be if we decided those parameters. But we didn't. The network does. Using a process known as backpropagation, the network makes a series of predictions based on training data and minutely adjusts its parameters to bring the predicted output closer to the expected one, repeating this again and again to become more and more accurate. By allowing AI to learn from examples and adjust its own connections, mimicking the human brain, we created one of AI's greatest strengths, but also one of its greatest failures. Because it's this very learning process that allows AI to learn to overcome any task given enough training data, even when we cannot define the precise decision-making rules that should govern its behavior. But this also means that because we didn't write those rules, we don't know them and we don't understand them. Even if we look inside the network, which we can do, we can look at every parameter, every neuron, every weight and bias. All we'd see are a series of decimal numbers, which are meaningless to us humans. The rules are encoded within the parameters of the network. Now, if all AI was doing was my homework and generating poems, this question of whether understanding why is important or not might be a purely philosophical one. But it's not. Among other things, AI is reading medical scans. A group of researchers built a deep learning model to detect pneumonia from chest x-rays. The model performed brilliantly in testing, but when they later applied interpretability techniques to understand what the model had actually learned, they discovered the AI was taking a shortcut. It wasn't detecting pneumonia at all. Rather, it was detecting the machine that took the x-ray. In the training data, portable x-ray machines, used for patients too sick to move, correlated with the disease. The AI gave the right answers for the wrong reasons, and without interpretability, no one would have known. Understanding AI is some of the most important research in the field. It can make AI safer, more trustworthy, and if used correctly, can massively improve future AI by reducing the risk of hallucinations and mistakes. This goal is what drives the field known as mechanistic interpretability, whose aim is to understand what's actually happening inside these networks, looking at the billions of parameters and weights, and understand what's actually going on inside, why certain outputs are generated and certain neurons activate. The early results are genuinely promising. Researchers at Anthropic, one of the world's leading AI companies, published work in 2024 demonstrating that you can find features in AI models that correspond directly to human understandable concepts. They discovered in one of their AI models the feature of the Golden Gate Bridge, and they published a version of their chatbot Claude where this feature was artificially amplified. The model became fixated on the bridge, bringing it up in unrelated conversations, at one point claiming to be the Golden Gate Bridge. Which sounds absurd, but the research is significant. Because if you can identify the feature that represents the Golden Gate Bridge and nudge its importance, you can identify the feature that represents bias or deception or a medical misconception, and you can eliminate them or remove them entirely. You can identify safety features and amplify them. You identify where dangerous behavior lives in the network and intervene. The EU has already passed legislation requiring high-risk AI systems be safety compliant. Governments are beginning to understand what researchers have been saying for years, that deploying AI systems that we don't understand in domains where they make decisions that are consequential for human life is simply not a sustainable path. However, the future of AI is bright. Interpretability has the potential to shape the future of AI, to make it more safe and more powerful. The future has a formula. It's being written right now, encoded in millions and billions of parameters across millions of training steps in every field, from finance to law to science. So I'd like to leave you with one final thought. The question that will define tomorrow isn't whether this formula becomes more powerful, because it undoubtedly will. The question then is whether or not we can learn to understand it. Thank you.